Alright, we're in for a long one. Hello, this is Counting Thermos by Scojo. It looks like a huge puzzle. The rules are pretty massive, and yeah, so this video is probably gonna take, well, at least an hour. I'm pretty sure I'm gonna spend at least an hour on it. So yeah. Okay. So I was actually recommended this puzzle by Lucian on YouTube, so I may or may not mention him in the video itself. But yeah, okay. Anyway, Counting Thermos by Scojo. Let's look at the rules of the puzzle. So this Sudoku is a little bit different. It is chaos construction. Place the digits 1 to 9 once in every row, every column, and every 9-cell orthogonally connected region. But you can see that there are no regions here, and the reason why is because the location of each region must be determined. So you have to have regions be connected by edges like this. So your region could look like that. That could be a valid 9-cell region, because they're all connected orthogonally. And for every region, basically, you have to kind of figure it out yourself. You have to figure out exactly where each region goes. So that is chaos construction. I've never actually done a chaos construction before, so maybe this will be fun. Alright, next we have thermos, which are, well, they are normal thermos at first. Digits have to increase from the bulb to the tip. So every digit here, the next digit will always have to be bigger than it. It does not have to be bigger by 1. It could be, something like this. So as long as every digit is greater than the last digit on the thermo, the previous digit. Right, and now the extra rules. Additionally, the digit in the bulb of a thermometer, so here we have 7 bulbs. The digit in a bulb of a thermometer indicates how many thermometer bulbs contain that digit. So these are counting things. So for example, this thing here, if it was a 3, for example, that would mean that for all the bulbs, there will be 3 3s. So they could be anywhere, but there has to be 3 3s exactly. And if it was like a 4, you need 4 4s. So something like that could happen, ignoring this clearly incorrect Sudoku rule over here. So digits here basically count how many digits in the bulbs contain that digit itself. And the digit in the bulb of a thermometer, so we're not done with the bulbs yet, indicates how many times it crosses a border, right? Because we're gonna figure out the regions ourselves, right? And each region is surrounded in borders. So, a region could, well, I need to draw a region. So a region could look like this, for example. And basically, the thermo will say, well, how many times does this thermometer pass through across a border, basically? And here the answer is 2, because it crosses a border twice. It goes into 3 regions at least. Well, it appears to go into 3 regions, but the answer is 2 because it crosses a border twice. So yeah, that is another thing that another thing that the digits in the bulb does. Let me just remove this now. Next, we have squares. Digits in a square indicates how many cells in the region are a thermometer. So for example, oh my goodness, let's say your region, I'm just going to remove all the colors first. Let's say your region looked like this. Let's say a region looked like, how do I draw a good region here? 6, 8, 9. Let's say a region looked like that. Okay. This digit over here indicates how many cells in the region are on a thermometer. So here you see we have 5 cells in this region that are part of a thermometer. So this digit will then be 5. Right. That is the squares. And finally, inequality. So this V shape between 2 digits points to a lower digit, basically saying that this digit is always higher than this digit, no matter what. Yeah, and those are the rules. Very long rules. I don't know how long I spent on this, like 5 minutes explaining the rules. But okay, I was told that this puzzle would be quite fun, so yeah, we're gonna be sitting in for a long one, so get cozy. Let us begin solving. So first things first, I barely know where to start with this puzzle, but I will have to assume it might be these two squares, right? And the idea is that these two squares have to be in different regions. If they were in the same region, then that same region would have the same number of thermos in them, basically, no matter what the region is, basically. If this region had like 4 thermos in it and this was in the same region, it would also be 4. And basically what that means is that these would then have to be in the same... these would have to be the same digit because it would count the same number of thermos. So clearly, squares adjacent to each other cannot be part of the same region. So let us begin drawing some borders to split them up. Now I also do know that every thermometer's minimum digit in the bulb is 1, meaning every thermometer must cross a region at least once. So that's something. This is a very small thermometer, and so is that actually, which might mean something. Okay, well let's do a bit of coloring first. We know this region, well, we don't know if it escapes in any direction, because it could all just be contained here. So I can't even say that these two are in the same region, or these two are in the same region. I can't do that. Okay. This one looks very interesting, because this one's at least a 1, right? So this has to at least, the region this is in has to be touching a thermometer in some way, even though it looks pretty far from any thermometer at all. It would have to do something like this at the very least, I guess. Okay. Right. Okay, I think I see something with this digit maybe. Because, you know, this digit counts how many thermometers are in its region. No, I don't think so. I was like, could this not be in the same region as that? And if it wasn't, it will have to cross region borders twice, which would make this at least a 2. But at least isn't really doing much here, because this could be like 3 if this was a 2, you know. And it could just spread all the way here. So no, I don't think so. Maybe we look at the ends of the thermometers, but that doesn't feel very fruitful either. What about the bulbs then? Because bulbs count, right? They count how many bulbs in total. I'm gonna color them. They count how many bulbs in total contain their digit. So if this was like a 5, you'd say 5 of them would have to have 5 in there. But I don't think it can be that high. Oh, no, they can't be that high. Yeah, in fact, all of these can have 5s on them. In fact, because the 5-digit thermometers can even have, you know, can be going all the way up to 9. So technically speaking, there could in fact be 5 5s on the bulbs if I wanted to. No, although they cannot, because a thermometer that is 5 long can only cross region borders 4 times. So there can't actually be 5s on any of these thermos. And in fact, yeah, because these thermos are at most 5 long, they can really only cross borders at most 4 times. Which means that every bulb here has to be from the digits 1 to 4. Right, okay. This thermo might also be interesting, because how many times can this cross borders? Can it cross borders 4 times? Oh, it can, can't it? And I was thinking that you could cross this 4 times. Because, you know, you could do something funny like this, and I think that still counts. Right? Because you could have, you could even have something like this happen. And this does seem to work. So, very unfortunately, yeah, that could in fact be 4. I mean, these shorter ones can't be 4. In fact, they can really only cross 3 times maximum. So let's just do that first. Right, well, okay, that could be 4 4s because like 5 of these arrows here. I mean, maybe it can't though. Maybe it can't? I mean, how many of these are there? 1, 2, 3, 4, 5, 7. 7 has to be expressed as the... Well, if you had 1, 1, 2 2s, and 4 4s, you'd make 7. So basically 7 has to be expressed as the sum of, some number of different digits, which cannot repeat. It could be something like 3, 4. Ah, okay. Well, if there were 3 different numbers in here, it would have to be 1, 2, 4, right? Yeah, you need 1, 1, 2 2s, and 4 4s. Okay, that does help. Because if it was 2 numbers that have to sum to 7, you would need 3 3s and 4 4s. I think that's the only way to do it. Which means that no matter what, you do need to have 4 4s here, right? Yeah, in fact, if you didn't have 4 4s here, then if you only had 1 1, 2 2s, and 3 3s, you only fill up 6 bulbs. Which doesn't work. So you need 4 4s. So four of these thermos here are actually crossing borders 4 times. That is very interesting. 4 of them out of 5. And so maybe we have to figure out which one is not doing that. Can this not do that? No, this looks fine. Oh, but in fact, if it was 4 4s and 3 3s, can we do something? I mean, this would be forced. This would be forced. This would be forced. Am I lagging? I think I'm lagging. Uh-oh. No, but that looks fine though. That really looks fine as far as making borders go. And then this could be the one that crosses 3, even though it appears that it can't cross 4. I think it could even cross 4 if it wanted to. Alright, and this one will be aligned, but that's not really gonna hinder us much. Okay. Although I do want to say first that in making regions, you can never have something that looks like this in your region. So your region can never look like this, basically. Let's make this, yeah, this is 9. Your region can't look like this. So basically you can't have a region that is separated by this random line here. That's not counted as border because these two are all the same region. So let's get that clear. You can't do that first. Okay, what else do we need to do? We know there's 4 4s. Which 4 does not work? I mean, okay, wait, that's a square, right? Oh. Okay. Well, I want to say that even if this happened, you can't say that, all of these are in different regions, because I think technically you could have a region that looked something like I guess something like this. This is fine as a region even though it crosses twice. It does cross twice here. So even though these were the same regions, I think this is still allowed. This is still allowed, I think. Okay. I really want to look at this again. Because this digit will be forced out here, which will be forced out to here. And then what? Anything about thermos doing extra random things? I don't know. Oh, not there. Don't draw a line there. Okay. So, oh, whoa. I didn't know you could do this. You can draw that. Wow. Okay, the pen tool has really been... well, that's new. Okay. Maybe I look at this one, which is a square. Because, I mean, if it crosses 4 times... This would need to see 4, right? Actually, it was a 4. 5, 6, 7. If it was a 4, all of these start to become quite restricted in their own digits as well, really. Whichever one becomes 4, then you can only have 2 options per thermal afterwards. After these become 4. Let's say that this one has to reach a thermal somehow because it needs to be at least 1. And this one... Well, if this one was a 4, I mean that doesn't look quite hard. Because I'm pretty sure it could do something like this. Or something that counts as a region of some sort. Or, you know, it could do this, and I guess that, if it wanted to. And that's technically already 4. Oh, I see, those repeat. There you go. These can both be 4. Which means all of these must be 4. There it is. There's 4 4s out of 5 here, and those two see each other. So they can't both be 4s, meaning the rest must be 4s. There you go. And wow, that does give us a lot of lines. What is this music? Okay, let's not worry about that first. Oh, sorry, this is not the right one. Sorry, these are the right ones. So look at this. Look at that. Crosses borders 4 times. Okay, so there is one more 4, which means one of these digits has to be a 4, wherever that is. Now, can this happen? Can this be a 4 now? Knowing that it must be the case. I think this still looks fairly okay. So, not gonna worry about that yet. But we can do a lot of coloring at this point. I'm gonna remove the green first and say that because this must extend outwards and this must extend outwards, I'm gonna use a different color. We can draw a line border there, which now means that this must extend outward and so must this. There's your line border. And, oh, we can do even more of that. Yes, because this one must expand outwards. It must, oh, sorry, wrong color. It must expand outwards again. And then this one must expand outwards as well. So we have even more to work with here. Now, see, this can't be in the same region because we already said your region kind of a random lines protruding out of that. So that cannot be in the same region. So we'll mark that as a third color. This will be a 4th color. And I guess by that one mathematical theorem about the 4 color thing, we can say that these are all 4 colors that we need. So let's use those 4 colors. That has to expand outwards. This one must also expand outwards, so we can do that. And now we can draw some lines. This one we don't know, actually, we don't know. But okay, this is very helpful. So this is no longer a 1 because it crosses borders twice already, so that's at least a 2. I like this a lot. Okay, this region could be in there, so can this one. But this one is definitely not the same region. Let's color that orange and must expand out. This must be in a different region. No, sorry, it could be pink once again. Okay, well, let's try putting in the options here. Let's good live here. This must be at least 5, which means, yeah, we have those options there. But I don't think this is going to give us much because the thermals themselves don't really do anything outside of being thermals once you stop looking at the bulb. Yeah, once you stop looking at the bulb, yeah. Okay, so I like that, I like that. It's actually been really fruitful so far, but whatever digit this is must appear elsewhere because it's not a 1. And in fact, 1 must just be on its own. Okay, sorry, that has to be orange because it has to extend out this way. So squares indicate how many cells in this region are on a thermometer. We know that, but we haven't reached squares yet with our region coloring. But this was very helpful. I like the 4. Okay, do we get anything with that? No pairs, no nothing at all? Well, I mean, that 4 we can also mark, I guess. I don't think that's going to give us much though. Yeah, it is not going to give us much. I can say that 1 can be there, so really 1 is in one of those cells. And, well, 2 and 3. 2 has to be in one of those cells. Three could be there. Alright, no, nothing yet. Okay, let's get through with this. Yeah, what do I do now? I have no other way of continuing this that I know of, basically. Except that saying 4s can't be here does mean... Oh no, I mean this could reach to that 4 and grab it. I'll say this region must have a 4 in it somewhere. And I guess it could grab this one. It probably could not grab this one unless it kind of tried really hard to reach around, you know, but I don't think so. I mean, it could do something like that, but that kind of just breaks the puzzle in and of itself, I think. I don't think we're supposed to talk about that first. Maybe this one might be helpful. I mean, these squares can no longer be 4, right? Well, this square can't be 4. This could still be 4 if it touched a region, you know, without a 4 already in it. But there's nothing in the rules that say that, you know, every region must have a thermometer in it, or every region must have a square in it or anything, so... A region in a square indicates how many cells are a thermometer. Yeah. So this region doesn't need a square in it, doesn't have to go all the way here or anything. Well, these thermals are placed in a way that they really just don't interact with each other at all. Like, look at those cells. They basically see nothing. I want to see if this was orange, right? Like if orange went down here, it kind of does force everything to follow going downwards. Which might mean something, but this feels possible. Well, I do notice that... Could that be a 4? I notice that none of these cells can be 4s first, because none of the cells are 4 and this 4 sees both cells there. So this region must hit a 4 somewhere. Which could be that cell. Could be anywhere else. Could it see like a 4 there or something? I mean, yeah, I could see a 4 there. Actually, let's think about these two cells maybe. Those just can't be in the same region either. Well, we weren't really thinking about this one as a region in itself, because that's really absurd. Okay, this one must touch a 4. Where can it touch a 4? 4 can't be there by regular Sudoku. There are no 4s in itself so far. And, you know... Well, it could grab this 4. Right? It could. And I feel like it should. It will. But you could technically also have a 4 here or here. Right? Yeah, so it could grab this one over here and have 4 thermometers in it already. Could also do that and grab another thermometer. So I guess that's fine too. I feel like we should. I feel like we should be able to figure out which one does this even work. It should, shouldn't it? It should work. I mean, not that it should, but it could work. Basically, what I'm saying. Now, if this happened with the 4, I mean, this doesn't do much better either, because we can't really say anything about this other than just putting lines down. We can't even say that this has to extend in either direction. But also, yeah, okay, wait, no 2 squares can be in the same region. Am I right to say that? Yes, because if any two squares were in the same region, they would have to contain the same number. But then that fails because they're in the same region already. So really, no two squares can be in the same region. 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, and we have 9 squares. So each square belongs to its own region. And therefore, every region must have a square. Yeah, okay, that's it. That's it. That feels good. Every region must have a square. Because there are 9 squares, and no two squares can be in the same region. There you go. Wait a minute. No, but digits can repeat in squares, yes. Digits may repeat in squares. It is possible for 2 digits to have 4 thermometers in them, for example. But no two squares be in the same region. They're not the same. That's not saying the same thing, because yeah, no two squares can be in the same region. Let me get this straight first. No two squares can be in the same region, and there are 9 squares. Therefore, each square has to be in its own region. And since there are 9 regions, each square is said to be allocated to each region, and therefore each region must have a square in it. Okay, happy with that logic. Now, how do I do this? Does this region have to touch any square? It clearly can't touch this square because it would break by having way too many cells, and also this would be isolated. It could touch that if you went this way. It could touch this, but could it really? And the answer is actually, I think it could. It could if the blue region went ahead and touched this square or something like that. But the blue region can never touch that square, because in doing so, you would essentially block off this green region. And in fact, the green region must touch a square as well. This is very tempting for it to touch, but it's definitely possible for it to touch this square. And it's also possible for something like this to happen and for something like this to happen. Okay. But these 3 squares in the same proximity does mean something maybe. Can this be orange? Can it? Can it be orange? I don't think so. I don't think it can be orange. If it was orange, this green will be forced to take this square, right? I mean, could it take that square? Crap, I think it could. Oh, it could, I think. Ugh. That's mean. Also, I feel like to take this square, you'd have to touch it like that, which kind of blocks this blue region. And you can't... Oh, could you do that? 2, 4, 6... Oh, you could. Then green could do something like this. Green... And then blue could do something like this. And then, pink could do something like that. And then these are all so far. Well, then this one is blocked, actually, because it can't touch another square. Oh, that is very far thinking ahead. I don't think that is what we can do. But that was my argument that this can't be orange. But could this be orange? Yes, it could be orange. You could do that. You could do... Oh, wait. Well... Alright, let's make this a bit more clear. What can this touch? It has 5 cells in its region already, so it can really only reach out 4 more cells to touch something else. Therefore, it cannot touch this square, for example. It can't touch that square, and therefore it can't touch that square either, because you can't cross a square to touch another square. So it can only touch one of those squares. And it must touch a square, we know that. So one of those is part of its region. Can we say anything about, this being part of its region? I'm gonna remove all the color here. But can this be in its region? And I think the answer is yes. Because, I mean, that would probably be shaded. You can't go hit there any other way. But this blue could now reach down to that region. That does take 9 cells, which is fine. This green could take that region, and this orange could... Well, this green would need to extend out this way. It can't touch any of the other squares. But the orange could really just do that, and then we'll be all fine. So the answer is yes. Pink can touch that region. Can it touch this region? To do that, I mean, it could take multiple different types of paths. It could do that, or it could do that. Well, it can't do that because of the 4. Okay. So to get to this one in 4 moves, you'd have to do this then. Which I think really all just means that that is always in its region. Yeah, and the reason I can now prove that is if it was not in this region, then this would have to happen. How would it reach something now? Oh, this could be in its region. I mean, no, if this is not in this region, sorry. Let's do this by counter argument. If this was not in this region, it would need to do that. This makes a lot more sense. How would it now reach a square? It could only reach this square. It can't reach that square by going around it. But in reaching this square, taking the minimum cells, because it must take the minimum number of cells, it will touch another 4, which it already has in its region. So what that means is that I'm pretty sure this must be in its region, which gives us more colors. Yep. Yeah, okay. This must be in its region. Yep. And then now green is forced out, which now forces orange out. But that's not the important part. The important part is that green must now have a square in it, and that is the only square it can have. So that's cool. We have the green square. And in fact, we do have the... Sorry, this doesn't have to be. Okay. So, yeah, this doesn't have to touch that cell. It could go this way. But this looks very useful in saying that there must definitely be a pink region here which affects everything else diagonally upwards. What about this one now? What can it touch? Can it touch that? No, because in touching that you have to avoid this, and minimum you can take 5 extra cells, which would put 10 cells in your region, so no. It can also take that. That is one thing it could take. It could also take this cell, which is something. Okay. Is there anything wrong with taking this? Is there anything wrong with taking this one? I think thermometer wise it becomes very restricted because how many cells are seen? 1, 2, 3, 4, 5, 6, 7. So this has to be 7, right? And then that will have to be 8, but 8 is huge. And how do you have 8 thermometers in a single region? Can you? And in fact, yeah, one of these has to be a 9, right? No, sorry. Digits can repeat along a thermometer. Sorry. So no, but this 7 does force that to be an 8. And how in the world would you even get 8 thermos to be in the same region? I don't think that's possible. Unless you tried something like really random like this. But no, yeah, because you can't take all of these, definitely. And in taking any 2 of these, which have to be at least 2 cells apart, because you can't take 2 adjacent cells, they're already separated by a region. Well, no, we don't know that. We don't know that because this doesn't have to be a 4. Right, so this could be an 8 if it, somehow did something random like that. Well, no, it could do something like this, I think. That is a feasible region with 8. Yeah, this is a feasible 8 region. If it crosses the border here, making this a 1. Yeah, this is a feasible 8 region. Which means it's possible. It's possible. Means we can't say this can't be an 8, which means you can't say that can't be a 7. Okay. Well, shucks. That is not something we can do then. I find that would have been a very good idea though. I think this we can knock this down to 2 options though. Because if this took that cell, then this would have to take that cell, in which case it will be 7, 8. Sorry, wrong color. In which case this would have to be 7, 8 like that. But if this did not take this cell, then what it would have to do is it would have to go this way, doing that. In which case this would definitely just be 1, 2, 3, 4, 5, 6. So in fact, I think this cell is always either a 6 or an 8. If it takes this, then this is 8. If it takes this, then this is a 6. Because in taking this, you basically see all blue cells in the region, which has 6 thermals in it. So this is either 6 or 8, meaning this has to be 7 up to 9. Now this has to be 7 or less. But we don't actually know what touches this one. right? Because this could be touched by, you know, this orange region maybe if this pink touched that. So alright, fair enough. But okay, so this could be, or this could be 2 or something. This could be a lot of different things. But we have a lot of digits going on, so I'm happy about that. Let's see if was this a valid 8 region? It is, right? Oh no, that's a valid 8 region. I mean, I don't think so though. I don't think that's a valid 8 region. No, I don't think so. Yeah. But that really is just so incredibly cursed. That is so cursed. I don't want to say that this can't be an 8 region, but I know it can't. And let's redo this entire thing again. Can this happen? If that happens, this must be 7, this must be 8, that must be 9. Now, how does an 8 region work? 8 can really only take 4 cells out of this. Ah, but it could do that. But also when taking, okay, so this 8 region can really only take 4 cells out of these 5, because this must have at least 1 border cross. So maximally it can take 4 cells here. And if we assume these 3 cells are all in the same region, it could then take 7 cells here, which means it must at some point take 1 more. If at any point this 8 takes 2 cells that are not adjacent to each other, say those 2, or those 2, or those 2 somehow, it would need to cross empty space. And in fact, I have to cross at least 2 cells of empty space, which it cannot do. So that means that it must grab a contiguous set of thermos from here. And that contiguous set must include, doesn't have to include this. Yes. Because if it did not, it would have to include these cells, right? And in doing so would have, at the very least, 1 empty cell to bridge the gap. Now what that means is that this is the only empty cell it has. Every other cell must be able to be touched without crossing an empty cell. Every other thermometer basically that this 8 region touches. So what that means is that, well, that's not possible. Yeah, that is just not possible. You can't reach any thermo like this. And so then it must reach that cell, which means what? If it crosses something like this, for example, well, wait, no, yeah, if it's that, again, we know this cannot connect a non-adjacent cell, so it must contain some contiguous number of cells, and it can't contain just 1 cell, so these can't all be part of a different region, because this clearly cannot reach 8. You can, you can't grab, oh, could you do that? You could do that. If this happened to be a 4, that happened to be a 1, I think you could like just very barely eke this out as well. This is another 8 region you could have. I don't want to say that that's very annoying, but even in that case, oh no, because that could be, yeah, even in that case, what happens now is that how many squares can you really have in this whole section here? And the answer is, well, right now there's 3. But this is clearly more than three regions can fit. Because 3 regions is 29 cells, and what? 16 here, 18, 20, 22, 24, 26, 27. Yeah, so this is more than 27 cells already. What? Can this happen? I mean, it could though, right? It could. Well, no, okay. Right, okay, let's think about not this 8 first. If this happened, Yeah, if this happened, I don't think it'll work. Because that would need to be a completely different region. Sorry, not red. Let's make it green. But this does not work. Yeah, this does not work. Because this region and this region both need a square each. And no, none of these regions are gonna reach all the way here. Ah, could it reach there though? Could it do that? Man, I think it could. Yeah, I could do that, couldn't it? Okay. Fine. Fine, I guess it could. Okay. Let's not talk about this then. I'm getting tired of this region being there. What else could we even do then? I mean, I keep saying there's nothing to do, but I'm constantly eking out some logic here and there. I'm pretty sure eventually you just have to land on something. I think it was very nice to know that I think it was very useful to know that every region must have a square in it. That is what the square rule basically falls into. And I keep repeating that because I think that's very good to remember. Alright, so maybe let's do a bit more of what if that was a region? This one already sees a square. So this region can't touch another square, we'll have to reach out like that. Which means this would have to happen here. Which does really mean that it's always just another region in and of itself. But, I mean, couldn't that happen? Could it? Because that forces that, which forces this. Oh, that breaks. Right. Okay, so it can't reach this square. Because if it did, the green would have to escape out this way, the blue would have to escape out this way, which now completely blocks purple from reaching any square. It can't reach this square like this or like this, and we know this already failed. So in fact, orange cannot reach that square and therefore must reach this square? Yes, because it can't reach that square, otherwise it will block this off. It can't reach that square and it can't reach that square. Yeah, those take too many steps. So it must reach that square. Meaning that is its own color. Let's make this pink for another region. I hope these pink don't touch each other. But yeah, okay. Now this could still be orange, right? Nothing that says that. Well, no, wait. Could this be orange at all? Because wouldn't that break the puzzle in the same way we did? Yeah, that would break the puzzle in the same way. So this can't be orange at all, which means that there must be a border here. Therefore, this must be region. Which gives us 6 so far. It does need to see 2 more. Or 3 more, sorry. Does this have to escape in some way? Could it escape like this? Or no, yes, could green go down then? Because we figured out that orange going down forces green to go down, which breaks. But green, yeah, well, yes, if green went down, it can't take that cell because it is a border. So even if it did take that cell, it would need to go down again, at the very least, which breaks it in the exact same way. So what that means is that green can never go down. And therefore, green is now forced out this way. Okay. Could that be another region again? I think it could. You could have something like this, and then this, and then this. But okay. That feels good. So we do have a region border here. Now, this doesn't have the power of purple because I keep confusing pink and purple. I don't even know what color that is. Is that pink? Whatever pink is, it is not forced to go down here because pink could do something like that, with orange going down like that. So yeah, this still looks okay, but okay, thank God we're making some progress. I like how all these regions so far appear to be one-cell white snakes. I mean, like most region puzzles, I think do use this idea that one region forces the other region that is stuck inside of it, which generally lends towards snakes. But that's not really the point here. Now, okay. Right now it sees 5 different things. If it hit there, that would need to be a 7. But if it hit this one, right, if it hit that one, oh sorry, if it hit this one, then blue actually forces its hand because you now have 7 so far. You need to see 2 more. You can't see those 2, and I don't know if that is allowed to be in its region. But either way, if it was in its region, then you'd have, you know, 6 thermos. If this was part of its region, you can't have both of these be in its region. So either it does this plus an extra cell here or here, it does not matter. That will land it to being 6 thermos. If it took this set over here to make 9, it would again see 6 thermos. So wherever, if it landed here, this would be 6, I think. Does it say anything about this landing here? Does this do anything then? I mean, yeah, it sees 3 so far, but this could also be a pretty low number, couldn't it? Actually, no, this would be forced quite a bit as well. Because this has to extend it this way at the very least, which will have to extend that way at the very least. 2, 4, 6, 7. Yeah, okay, let's do a little bit of ideation here. If this cell was taken by blue, this would have to be purple's path. Pink, whatever. Now, this blue is forced, right? Because 2, 4, 6 so far, you need to see 3 more. And therefore this can't be not blue, otherwise it would be stuck with 7. This can't be not blue, otherwise you'll be stuck with 8. So in fact, those have to be blue. And then by default, because this is, well, not in any other region, we know that that has to be blue itself, giving us all 9. Right. Which means that would then be 5 if blue took it. But we know if pink took it, then by blue's method, or by blue, that would happen. And in fact, this would then become a 6 no matter what other path we chose. So I'm pretty sure this is either a 5 or a 6. But more importantly, we can also say that in both cases, these 3 cells are all part of the blue region. And that is very cool. Because that now means, well, that again could be part of its region if it saw. No, wait, yes, wait, sorry, what? No. This could be part of its region, in which case it would see 6. So if it hit that cell, it would need to be, does it have to hit one of these cells? Yes, because it can't hit any other cell. And so that means that whichever cell it hits, I think we can place borders here and here. And we can also, well, we can't place a border there because, yeah. So either it grows out this way or it grows out this way. Which means, oh, I was gonna say which means there's no border. There could be a border there. There could be a border there. Dang, okay. Well, that seems pretty helpful. Okay, now what? Yeah, this could be its own region in and of itself, so I think that's fine. Could this one... okay. I was wondering if, by any chance, this could somehow... I don't think this can reach that square. Yeah, because in doing so, what it does is it forces some of these to be the same region, right? In touching this square, you sort of block it off. And so these three regions have to either be pink or purple because they can't be blue. And so these three regions are always going to have 2 pink and 2 purple somewhere. But this... yeah. So if this reached that square, then it would need to reach there somehow. And let's just randomly draw this set here to show that. This can't be orange, so it must be pink then, because it can't be blue either. And so that would have to be orange, and then that just would have to be pink, which doesn't work. Because we know pink now has to reach that square, which then gives it too many pink squares. So I think that orange cannot reach that cell. And I think the idea is very similar if it reached that cell. In fact, it's even... is it even worse? I think it might be even worse. Although I'm not sure. Because... yeah, it's basically the same idea where none of these can be blue. And therefore, you need something like this. Which means that pink can no longer reach this square, which means pink must reach that square, which again fails. So orange can't reach any of these squares because it would kind of block pink to be inside. So that means that orange must take this square. It can't take any other square as well. Yeah, because that just takes too many steps. And this one, well, you can use the same logic as pink, but I'm pretty sure, pretty intuitively, that can't be orange. It blocks pink in way too much. So that's orange, which is something. But I mean, at least we figured that out. We have figured that out at least. I was wondering, could this be a new region? And I think it could. It could have a, you know, it could have a new region that looked like this, if it wanted to just keep pink inside. Yeah, that works. Okay. But this could also be pink if you wanted it to be. You could do something like that, and then that. And then this could be our new region. So, I don't know what else we have then. Yeah, I mean, we know these can't both be pink, but they can't be orange either. And because if that was orange, it would have to be here. Which means that it would have to touch one of these cells, yeah. So, one of these regions has to be, they can't be both pink. Can they be non-pink at all? No, if they were both not pink at all, then this one would have to reach all the way out to this square, which puts 2 squares in this region. So they can't be both non-pink. So they must have a pink in there. And therefore the other region, which they can't be both pink because of this line here, the other color would have to be some other region. So we can sort of do that. Sort of. And now say that this is pink. I could still go down there. And if it went up here, this doesn't have to be pink at all. I was like, is this pink definitely? No, because it could do that in your new region. Okay. This does look pretty small. If, yeah, this has to see... could it do that and see 3? I think it might be able to. It could see 3 thermals like this. It could see 2 thermals like this. And it could see 1 thermal like this. So I guess this could be 1, 2, or 3, but it can't be any greater than that. And this one would see quite a number, I guess. Okay, well, this is stumping me quite a bit. Right, sorry, okay. This... Oh, don't we have this already? We have that. It crosses it once only. Okay, right. This digit. I almost forgot. A number in the bulb says how many times you cross a region. And we now know that it does not cross a region here. So this has to be 2. Which means there has to be a 2 somewhere else. And there also has to be a 1. So none of these can be 3 anymore. And the reason is because, yeah, it's 4, 2, and 1. You need 4 4s, 2 2s, and 1 1. Okay. Okay. So maybe that's what we're supposed to think about, because yeah, I don't know about these two being in different regions. Can they? Yeah, I mean they can, because if you did this with pink, then you could do... Well, let's think about that. If you had sorry, if this happened, then you basically need this, and then you need this to be part of blue, because and then you'd have this, which fails because your thermal can't cross 3 borders. Ah, okay, that is actually way easier, which means that it cannot take that cell, it must take that cell. Which now means blue must take that cell. Which means something. Yeah, and if blue takes that cell, then it's just a 6. So we have blue, and we have another digit. Very nice. Thank you so much. This still could be 1 or 2 depending on whether these are in the same region or not. But in fact, if they were in different regions, how does that work? It could work if you had something like this. Right. Okay. Yes, they could be in different regions. They could also be in the same region. If you had something like this, that's also fine. Okay. Fair enough. I'm happy enough with that though. Let's keep those numbers again. This one... 1, 2, 3, 4, 5. Well, this one has to be a 6, right? Because he has to see one of those. We know those can't both be non-region, non-pink, because it will force pink to go down here. So this always has to be a 6, I think. Which doesn't tell me anything about that, because they don't have to be in the same region. But in fact, because one of these are a 6, if these two are in the same region, then this is just 5. But if these two are in the same region, then this would have to be a 7, 8, 9. 5, it sees one of these, and whatever else it sees. 2, 4, 6, 7, 8. This is the 8th cell. And its last cell, if it was here, it would have to be there. If it was here, it would have to be there. It can't be both here and here, because then this cell would be isolated. So it would have to be one of those cells that were the last cell. Yeah. Okay. 6. I mean, 6 here does restrict that, because if this was a 4, you need 5, 7, 8, 9. 5, 7, 8, 9, 8, 9. No, nothing of the sort. Alright, this 6 means that's a 5 by just region on its own, so let's do that. This one is bigger than 2, could be a 3. Can't be 4, 5, or 6, could be 7, 8, or 9. Oh, but we know 2 is no longer in those cells, 2 is not there, so 2 must be there, and that gives us another digit. Which doesn't say anything, but we know those are... Well, those need a 3 somewhere. 3 could be there or there. Same with 1. And in fact, 1 and 3 must be in those cells, which we already know. Ah, in this row though, 5 and 6 can't be anywhere there, because 5 and 6 are already in this region. So 5 and 6 must be on this thermal somewhere and can only do so like that. So more digits, thank you. Now I really just hope I did not do anything wrong with my logic here. Because that would probably force me to like restart the entire solve. We're already in so deep. We're already in way too deep. Okay. What now? What now? What now? This digit can't be 2, so it has to see another thermal at the very least. Which is probably gonna be one of these cells. I mean, it goes to be that one though. I mean, maybe now we can start rethinking about whether this could be a 4. Does that break? I think it breaks this one. Yes, it breaks this one. Right, because if this was a 4, you need something like that to happen. That's forced. Now, how will this escape? It cannot escape down here because green is already blocking it. So we need to escape down here because it can't escape down here either. There's no escape there. So we need to escape down here. What does that mean? That means that this section over here, it can't be any of these colors. So this will have to be on its own and therefore isolated, which doesn't work. So that means that I think this can't be a 4, which means I think that's a 4. Which, I mean, that feels a lot more. That feels a lot more giving, basically, what I'm saying there. So there you go. This feels a lot more less restricted. So yeah, it's probably the right answer, even though I had to prove it by first contradicting with this being a 4. But okay. Now this clearly has to be at least 3, because it can't be 2, it can't be 4, it can't be 5, it can't be 6. Whoa! So this is either 3 or a lot more than 3. And can it be more than 3? If we took the minimum 7, well, there's already 4 empty cells here in its region, so that doesn't work, which means that this can't be that big. If it were, yeah, it's minimum 7 if it's not 3, and you can't have 7 in this cell because it has already 4 empty thermometers, meaning at most you can have 5 thermometers in this region only. So this is definitely a 3. So it must see one more thermal, even though I don't think we can tell which thermal it sees. It could be this thermal or that thermal, right? Yeah, it could reach all the way there. But it must see exactly one more thermal. Okay, that's very good. This now can't be... again, this could still be another region if I did this, right? So yeah, no, I don't think that's how we do this. This has to be its own thing, but could be a different region from that. Although this does look very weird though. Because if something like that happened, right? I'll make this like a blue or something. Then what? Then this will have to do that. Can't go into its own thing here. I would have to wrap around, which does force orange here, but I think... Oh, does this work? Does this barely work? I think it might. I think it might barely work. Alright, I think it might... Well, 1, 2, 3, 4, 5, 6, 7, 8, 9... Yeah, I think it might barely work if you did something random like that, and you know, that could happen. So, that's fair, that's fair. There's a huge deficit of squares in this area, which might be interesting. And we know this is no longer pink or blue, and it can't be orange clearly. So let's make this a green for this region, whichever comes out to there. Oh, sorry, I was not gonna make this blue either, because we don't know if it's the same region or not. Weird. Alright. Well, actually, this has to be quite small. Because what can it really see, right? It sees one of these. Even if it sees all those, it can't see... I mean, it could see that, couldn't it? It could. So I guess... No, because it's 6, yeah. So this is 2, 3, or 5. There you go. 2, 3, or 5. However, this region is stuck in here, basically, and must escape by one of these cells. Which means it must see another thermal in addition to this, and in addition to this. So this has to be at least 3. How can it be 5? Yes, it can be 5 if it took something like this, plus a few extra cells. So yes, it can be 5. It could also be 3 if it just tried, you know, to avoid everything like that. I don't know, like this maybe. 3, 3, 3, 3, 3. Yeah, if it did something weird like that, yeah, then it could be 3. So this could be 3 or 5. And I guess that's that then. Okay. Fairly interesting. I still don't know what I'm supposed to do though. Okay. Let's think about this. Can this be 5, 7? Can none of these be 6? 5, 7. Yeah, I think so. I mean, that could be 6 if it did something like this. 6 here could see that cell, but I don't think it really matters. 5 can't be there. 2, 3, 4, 5. Yeah, this could be 5. Can't be 6. But we could take the minimum 2, 3, 4, 5 here. That would work. 1. Oh, well, yeah, okay. So, no, wait, no, this is not it. Sorry. We have so far all of these cells that are part of the region. We have that cell, that's 7. So we need 2 more cells. It's either here or one of these. It's here and one of these cells. Which must be where the 1 goes, because 1 can't be in any of these cells, right? So wherever the 1 is in this region has to be in somewhere there, those 3 cells. Somewhere. Can we do anything similar, like... what about 3? Oh yeah, 3 is very similar in fact. Yes. Yeah, okay. So 3 can't be in any of those cells because you couldn't have anything between 2 and 3. And we know none of those cells are 3. This 3 actually sees that cell. So wherever 3 is, it will be there, which sees this cell. So wherever 3 is, this is not 3. So that's 5. Wow. Okay, that was very clean. Now how does 5 work? It sees 1 here, it sees that, and we need to see 3 more. Could it see this? It could. Okay. What else could it see? I mean, it could also see that. It could see that. So I think anything is fine with what it sees. Does it have to hit that cell? To see 5? To see 5? Yeah, I think so. I think so. To see 5 in this region, it has to hit this one. I think. So I'm gonna try to make it so that this 5 does not see that. What happens if so? Or this 5 will be forced out there, which now means that this has to be where the region comes from. Oh, whoopsies, wrong colors. Which means that this has to be pink, but basically that is your green region. And now how will it see 2 more without seeing that? It can't see that because in seeing this cell, it would loop over and isolate this one from being part of any region. And so if it can't see those, then the very least it could see are those two, because we know those are all in different regions. But it cannot see that cell because we need to reach really, really far. So I think that there is no way to make it not to touch that. So I think that happens. Which means this is a 1, which means that's a 2. Which is what I think. Don't know if that's right, but I think it's right. I have a little inkling that it's hopefully correct. Oh, so now, if this region hit that one, how would that work? You'd have this happen. Oh, and then, well, no, this could be orange, right? Or like this couldn't be anything, but no, it could still be orange. And then orange could be like that, and then green could just take all those cells. 6 here, 7 here, 3 here, 8, 9. Yeah, that's fine. That's fine. I mean, okay, what if that was a 5 then? I mean, then these would have to be... No, I don't think I can do anything with that. Still not exactly sure though. So, yeah. Okay, let's just mark in the options for this then. 1, 3, 7, 8, 9. This can't be 1, it can't be 9. If it can't be 8 either, because then you do that. If it's 7, you'd have 8, 9. Oh, right. Well, this can't be 7 then, because 7 here makes this 8 and 9, which removes everything from that cell. Oh, okay. So this can't be 7. That's just 3. Sure. Alright, freebie, which means that's not 3 now. So 3 goes there, which must be where the region leads. Okay. Very nice. I like that. So that happens, which means this. And now I'm pretty sure this has to be green. 6 here means that's 5. That could still be 6 or 7. But this now can't be 3, 4, 5. And in fact 4 here means it couldn't be 3, 4, 5 anyway. I think we should have seen that. 1 has to be there. This is now 7, 8, 9. This can't be 7, so 7 must be there, which sees that cell, so that's 6. And we already know that those are in the same region. Okay, everything's coming out very cleanly so far, so I'm happy with that. Sorry. Yeah, this has to reach over to here, and in doing so would isolate this out unless it was in its own region itself. So I'm pretty sure this has to be green. Yeah, and I guess another way to say is it was not green. Like, whatever 9 cell region you make out of this thing here, this cannot reach around it to hit that one, because you'll definitely take more than 9 cells to do that. Some perimeter thing, I think. Okay. Well, that has to be orange. Okay, we got a lot of digits. I'm very happy with what we have so far. Right, what now? I mean, it's already been 70 minutes. But I don't have much to show for. Although maybe that's just because this puzzle is huge. It's like I mean, I want to say it's a 2-stage puzzle, but it's not. Because you have to use both ideas at once. You have to use Sudoku, drawing regions, and a lot of random variants together. This is one, correct? Yeah, it crosses it once. This one crosses twice. But we don't know which crossing it does. Although maybe I could explain how. Let's think about if this was a new region, how would that work? Then this would have to be doing that. This one have to go out. I have to go out again, which means that you have one separation here. Then I have to go out. This one can't do that, so we have to do this. Ah, and there you go, broken. Whatever region that is. In fact, that region is forced to be orange, but even then, you do this, which then breaks this thermometer because it only crosses regions once. There you go. So let's go through all that logic over again. If this was in a third different region that wasn't either of these, it would need to escape out this way. This one would have to escape out this way because it can't do that, otherwise you'd block off orange. So we need to escape out this way. Orange would need to escape out that way. This would need to be that. This would need to be that. This would need to be that. But more importantly, this cannot be part of pink anymore because pink already has a square in it, which must mean that pink goes out this way, which fails because you no longer cross a border twice. There you go. So this must be pink, which means that is not pink. That is a... well, that could be orange, right? I guess so. But okay, pink definitely can't reach here because that would block orange off completely. And pink can't reach out here. So it is basically stuck at the very most doing something like this. Which means it must in fact escape out here. Which means green must in fact escape out there. Which means green already sees 7. Could see 2 more like that. Could see 1 more like that. Right. Okay, now let's think about which is the last thermometer this region sees, I guess, because it sees 5. Wait, it sees 4 right now, so it needs to see 1 more. Can it see any of these cells? To do that, it will need to cross over to do that, right? And by doing that, you would isolate this cell, which can no longer be part of green because green only sees 5. So in fact, green cannot see any of those thermometers because that fails. So this must be the thermometer that green sees. I realize in fact that this region here sees 4 thermometers. Don't know what that means. Don't know what that means. Oh, sorry. Can I do this? 6. Can I mark these options? Yeah, this 6 here sees that cell, so that's now 7, forcing that to be 8, forcing that to be 9. This is no longer 9. Okay, well that is something else, I suppose. This one can't be 1, could be 2, can't be 3, can't be 4, can't be 5, can't be 6, can't be 7, could be 8. So I think this is either 2 or 8, because it can't be 9 either by this cell. Okay. I thought it was almost a naked single there, but it's not a naked single. It is, well, it's close. It's close. Now, in fact, yeah, I think this has to be a 1, right? Because whatever region orange is, we know this is the same region. Can orange ever see any of those? To do so, you would need to very minimally do this, which definitely takes up more than 9 cells. Yeah, this takes up what, like 11 cells already. So none of these regions can see any of these thermometers, which means this is the only thermometer it sees, so that is a 1. Okay, so 4 in this column Can't be in those cells. This 4 sees that cell there, so 4 must be there. So this is either 2, 8, or 9, but can't be 8 or 9, so that's 2, that's 8, that's 9. Very nice, okay. This can't be part of green, because it already has a 4 in it. I don't know if it's part of a new color, maybe. Could it be part of a new color? If it is something like this. Very funny. I don't know. I don't think it could be part of a new color. It would have to be orange then. And this one, I mean, this one could be either green or orange. So I don't know. This cell can't be 1, 2, 4, 5, 7, 8, or 9. So this is either 3 or 6. Oh, in fact, by here, I guess you can say that this is 3, 5, or 6. Alright, fair enough. So if this touched into here, then this would have to be 3, right? I think it has to. Yeah, because suppose this was a new color that, you know, wasn't orange or green. What would it do? You need to touch a square somewhere, and the nearest square is there. And by doing that, firstly, you take up basically all 9 cells. Yeah, minimally, the minimum path you take already takes up all 9 cells, so you have to take the minimum path, which then again breaks this region, because we know, you know, this region cannot be just orange, otherwise orange would break. But it can't be any new region either, because there's not enough cells there. So I don't think this can be green. Sorry, this can't be a new region. Can it be orange though? I think it could. Your orange could do something like that. This could be a valid orange region. So yeah, alright, fair enough. Can I see this one? This one can't be 1, 2, 4, 5, 6, or 8, but it could be 3, 7, or 9. Okay, well, not giving us a lot of information here, so unfortunately I don't think there's anything there I can do. Alright. I see, in this column, where does 1 go? There you go. 1 can't go there. 1 can't go there, sorry. 1 can't go here by Sudoku. 1 can't go there because this implies that this has to be bigger than that cell. So that can't be 1, which means that 1 in this column can only be there. So there you go. Something to think about. Where does 2 go in this column? There it is. 2 can't go there, because this will have to be 1, which doesn't work. So 2 in this column can only go here. Okay. So now we have 3, 6, 7, 8, 9 to work with. But this could be any of those, I think. Yeah. I do notice those 2 twos, which are very close to each other though. Do they have to be 1 green, 1 orange? Could this be a new region in and of itself? I think this could be a new region. You could do something like that. I think that's okay. Yeah, I think that is okay. So this could be a new region. Doesn't have to be. But this one's weird. Oh, can this one be a new region? I don't think so. If it was, then minimally you need to do that, which does take up 9 cells. 2, 4, 6, 8. So that you need to take the minimum path, which then again breaks this area. So this cannot be new region. Definitely can't be part of green, because green already has a 4 in it. So it must be part of orange. So now those have to be part of orange, because they can't be any other region. This orange must see a 2 somehow. It could be that one, it could be that one. Oh, I know whatever this cell is, this we need to see as well, doesn't it? Yeah, so what does it see right now? It needs 7. It needs one of those, right? It needs a 2 somewhere. It needs one of those 2s. It can't have a 2 like out there, I think. Although maybe it could do something like this. But either way, this digit is not here. It's not here. And, well, it's not in any of those cells. So where does this digit go in this region? Well, it have to be there, right? Or there, or something. But in either case, I think implies that because there's already 7 here, you either reach here, or if you reach here, you need the minimum number of cells, which would be going straight. So I think that cell is always orange. I think it's always orange. I don't know. Which means that is not orange, is it? Okay, let's see if I can do this again. If this is orange, for example. Or, yeah, no, I think this is always... Okay, let's think about this. If this was not orange, then how does this digit appear? It can't be anywhere there. It can't be anywhere there. It can't be anywhere there. It would need to appear in one of those cells. Oh, could it do that? Ugh, I think it could. This is 9. So it could be there. Okay, fine. So yeah, I guess this could really, in a certain way, not be orange. So I guess, sure. Right. So, okay, let me think for a bit. I'll draw a border around the thing itself so it looks nicer, but I'm gonna go think for a little bit and I'll see what I come up with. So let me just stare at the screen right now. Let me just stare at the screen. What can we do with this information? So how many regions do we have? Let's think about, I mean, could this be green? Could this be 2, 4, 6, 8, 9? Yeah, this could be another region. I said that could be a region. Oh, although this 4, right. No. Any region here. Wait, that's so weird. Does that even work? Any new region here has to touch this cell. Oh, I mean, it could also, you know, stretch all the way over and do that maybe. Yeah. But this one sees 4 thermos. I did not remember that rule, but if it's in a square, it sees that number of thermos. So what that means is that this cell here sees 4 thermos. How would it do that? Well, it can't see that. It can't see both of these, so maximum it can only see one of those if it tried. It needs to see 2 more. And those 2 more would have to be supplied from this thermal, I think, because it can't grab any from that thermal without first reaching this thermal. So, what could it grab? I mean, it could grab this one and this one, this one and this one. It could grab those 2. Can it grab anything else? I don't think so. I don't think it can grab any of those, unless it grabs that first. So it can never grab that one. Okay. This is very weird. But okay, let's give this a new color before we start, so we can identify. And so I'll give orange. So let's give these cells new colors because we know they're all in different regions at this point. Does it make sense to say? Well, this has to be pink, doesn't it? If it's not pink, then how does pink even work? It can't go that way. It can't go that way. So at the very minimum, your pink is light down here and would then have to go this way, which completely breaks this thermal. So I don't think this can be non-pink. So that's just pink, which means, which does mean that the only way, yeah, so this has to be green, and 2, 4, 6, green already has 8. So its next cell must be part of a thermal, which has to be this one. That's the only one it can take. Which is a horrible color for me to use. Oh my god. Let me just change colors for a bit here. There you go. Colors are no longer messing up with each other. But there you go, that is your green region. I think this is forced. Which is maybe good. Yeah, therefore this 4 can't see all 3 from here, because then you wouldn't have 2 border jumps. Right? And therefore the 4, even if it sees 2 here, we need to see at least 1 more from here. Oh, but the issue is, could it see something like that? You know, could it do that? And then have blue do something like this? And then another region do something like that? I mean, it could, right? Yeah, it could. So that's unfortunately very not right. Although I'm pretty sure those two have to be orange. In fact, if this was not orange at all, how would this even see 4 thermals if every other thermal is already taken? So firstly, that's orange. It can't see both of those thermals, so even if it sees one of these, it would need to see another one, which would have to be there. So there you go. This one, well, I don't know. Okay, but let's give this a new color. Let's make this green now. I want to say that this can't reach here, because in reaching there, I mean, yeah, then this could happen, which is fine. Yeah, that's fine though. Okay, so it could happen like that. I want to give these shapes new colors, but I want to use 4 colors. I don't know why. I just think it's very weird. It's very funny if it did happen like that. Okay. So this one's already at least a 3. It does need to see 1 more thermal, at least, because it can't just be 3. So it's 4 or 5. Can't be 6, can't be 7, can't be 8, because you can't see both of those, and you need to have another empty cell, I think. And in fact, let's think about this. Must it extend out to here? I think it must, right? Because even if you take as much as you wanted from here, you can't take that cell, definitely not. And even if you took, you know, whichever cell you took here, you can't take both. So at maximum, I think this region can only have 5 pinks, which means this must extend here. So again, we now know this can't be 8 or 9 because we already have 2 empty cells. So this has to just be 4 or 5. Meaning it must see another, or at least 2 more, 1 or 2 more thermals. It could be those 2, really. Well, could it be those 2 though? Could it even see that? Oh yes, it could, because this green can save the day by looking into there, which allows, you know, orange to take up the rest of the space. So yes, so this could be pink. Fine. I'm gonna draw more things here. Oh, but we now know that all of these have to be different because these have no border jump. There's no border jump here. So because of the 2 there must be a border jump here and here. There you go, which means this is definitely in a new region. It is not in any of those and therefore must be... Well, could it be orange? I think... yes, it could be orange. It could be orange if green took all of those. So yeah, it could be orange. Fine. But at least we know this now. Okay, let's look at the options for the thermal itself. I think that might be useful. So 2, 3, 4, 5, 6, 7, 8, 9. So each of these have 4 options then. 3, 4, 5, 6, 7, 6, 7. Yeah, these are 3 options. This can't be 6 or 7. These can't be 6 or 7. This can't be 6 or 7. Oh, and this can't be 6. Ooh, very interesting. So that now can be 5. This, okay, this is everything. Oh, but there's an 8, 9 pair here. Wow, I didn't really see that. So that's really just 5, 4, 3, pushing a 1 there. This 5 means that's 4. Oh, so it only sees 4. Oh, in fact, oh, it could see either of these, right? No, but it can't see this one because it's either 5 or 6, and there's already a 5 and 6 in the region. So it must see that one then. Very cool. Oh, 7, 8 pair here means that is 8, 9. This one we don't know, but these form a 1, 4 pair. Oh, 4 means that's 1, means that's 4. And this 1 actually does tell us something because there's only one thermometer in this region, which I think makes a lot of sense. So it really can't go all the way up here, but it... Ah, in fact, yes, it must extend out this way, right? You can't block this off, otherwise this 1 would have to be forced up there, basically. And so in going down this way, it already sees 1. So then we do know that it does not see that one up there, which must be seen by orange now. Okay, which must be seen by green. So that gives us a lot more things to work with. Now, this must still be green as well, obviously. Okay, lots of regions down. Very helpful, very helpful. This one must also be region. So in fact, this blue is forced downwards, right? Yeah, 1, 2, 3, 4, 5. Even if it had all those cells, you need to see 3 more. So 1, 2, 3. Those 3 have to all be here. And now this green is forced into here, which I think is good. Everything does seem to be all coming together now, which I like that. I like that. Finally, this puzzle is... okay. So this one has to escape out there, which I think is the... Oh no, how many? 2, 4, 6, 8. Oh, and it has to escape out there as well, which gives it the entire region. This blue has to escape out here as well. 2, 4, 6, 7. So we need to see 2 more, which means that is this entire region. Which means it's really just this to work with, so that's fine. This should not be too hard. And after that, it should be just regular jigsaw Sudoku. Oh, okay. Let's mark those down. Those must have an 8 in them. 8 can't be there or there. Okay, 8 is one of those cells. Okay, let's try to solve this one. How will we resolve this? Now one of those twos, well, those twos we know are now 1 orange and 1 green because they can't be in any other region. Can this be orange? Oh, sorry, I switched the colors a bit, so... I mean, that could be orange. This could also be orange. Okay, well, can this be green? I think so. I think so. If it is something like that. Yeah, that's fine being green. Okay. And really, because there are no thermals here or anything, I don't think these numbers will help us anymore. So that's unfortunate. But also it at least tells me that whatever I'm doing is probably... Okay, so this is 3, 6, 7, 8, or 9. Okay, never mind, that does not help. That does not help. Alright, no, we can put this digit down, that's 3. 3 because it sees 3 of those. Which means those digits are 1, 2, and 8. Yep, and this 1, 2 pair here makes that an 8. It's not really a pair, it's just 1 and 2. This 1, 2 gives us our last 2 digits, which are 3 and 8. This 8 means that's 8, that's 3. Okay, yeah, normal Sudoku seems to be the right way to go. This 8 actually sees that cell, very funny enough. That's 7, that's 7, that's 6. Okay, so those digits have to be 2, 9, 2, 6, 9? 9 come in those cells, so 9 goes there. This is 2 and 6. 6 sees that cell, so that's 2. That's 6. Okay. 7, 8 pair here makes that a 9. Sorry, I just blanked out. What are we doing again? This 9 means that's not a 9. 3 or 7. Okay. This is 1, 2, 3 or 7. This is not 3 or 2. That is not 1. Okay, not very helpful, but thanks for trying. Yeah, 1 here sees those cells, these 1 see those cells, so 1 must be there. In fact, this 8 sees that cell, so that's 7, that's 8, that's 9, that's 8. This cell must be 8 by this 7 in the same region. This cell is a 5 to complete the column. Those cells are 2 and 7, which this 2 disambiguates. 7 here, 2 there. 7 means that's no longer 7, which doesn't give us much still. This 5 means that's a 6 now. Those digits are 4, 7, 9. This can't be 4. This can't be 7. That can't be 4 as well, so 4 in this column can only be there. Can this not be a 9 either? No, I mean, it could be either, I think. I don't know, I wasn't really paying attention. 5 can't be in those cells or those cells, so 5 goes there. This must therefore be an 8 to finish the column, row. This is 7, 8, 9. Yep, and this 8, 9 means that's 7, so that's 9, so that's 8, so that's 7. This means that's a 1, that's a 2, that's a 3, that's a 7. This 6 means that's now a 3. That's now a 5 to complete the row. This is a 7 to complete the column. This is a 1 to complete the column and the box. This has to be 2 and 9. 2 must go there, 9 is there. Those digits are 5 and 6, which we can resolve. 5 here, 6 there. That's 3. This is... oh, 3 in the corner. That, I think that's... oh, this is 2 and 6, so 2 goes there. And well, 6... well, no, wait, what? Wait, no, that's not 2, 6. Sorry, I just jump scared myself. This is 6 and 9, sorry, and this is 6, so 9 goes there. But before I put 9 down there, let's take time to finish this region first. Right, because we got to. So 7, this 7 cannot be part of green, so it's part of orange. This 3 is not part of green, so it's part of orange. This 9 is part of green because it's not part of orange. This one must be part of green, therefore that's part of orange, giving us our last regions, and finally allowing us to place a 9 as our last digit, solving the puzzle. Oh, an hour and a half. 3,000 solves? That's insane. Whoa, okay, so this was a cool puzzle. Wow, I really love this one. This was amazing. Okay, so I hope you enjoyed that puzzle. I definitely enjoyed this one. Yeah, I'll see you next time. Bye bye.